Perfect. Thank you. Appreciate the opportunity to present in front of you all. I was not able to make it in-person meeting because of the last minute schedule change, but I am honored to be here through Zoom link, and it's my pleasure to spend next 20 to 25 minutes talk about what kind of activities going on in our lab, more importantly on cold plasma. Professor Shashi talked about a lot about food security. I think it's very difficult to give a presentation about food safety immediately after the food security because no matter what it is, people need to have food, and then we can talk about the food safety. But this is just an opportunity to educate our students, our next generations, so that when they go into their career, they will be able to also think about the food security and also food safety. Food security comes because of we waste a lot of food, whether it's a um, developed country or developing country. Developing countries waste food. We are not able to store them, transport them more effectively. Developed countries like USA, we waste 40 to 50% of the food after processing it. So we waste a lot of time and the energy and the money in processing these things, and then we waste it because it's plenty of food here, and people tend to waste the food, and whether they want to eat it or not, they will still have the full plate, and then they will throw 40% of it. So much for the food security. Let's get into the food safety aspect of it. Um, I think most of you know about food safety. There's a lot of methods available to inactivate the microorganisms. Um, Even though I am giving a presentations, most of our work was done by two graduate students. They are listed here, Tejasvi and Rajesh. And Ren Yang is the new faculty in our department, um, who is the major advisor and dissertation advisor for those two students. Um, there's a lot of outbreaks in US and throughout the world. Um, we are going to focus on two different microorganisms, Salmonella, and also I'll tell you about another microorganism we are working on it. There are about 551 cases. If you look at the numbers, these are all very 3 to 4 week delay in case of reporting it. Uh, so true numbers will be illness will be higher than the reported. Um, when we talk about salmonella outbreak, most people recover without seeking medical care or undergoing testing for salmonella. There is also outbreak in chocolate industry 2022, mostly linked to the Kinder chocolate has sickened more than 450 people. Children like this kind of chocolates because it's very attractive, and it's also in egg shape. So this outbreak has hospitalized higher portion of people, mostly children younger than 10 years of age. So when they get sick, there's a lot of revenue lost in both by the parents and the children's. Um, and these salmonella strains are very effective. Six different antibiotic resistant to six different antibiotics. So it's very difficult to um, kill these microorganisms. Um, there's also outbreak associated with peanut butter. People like peanut butter, but here in case of 2007, there were a lot of outbreak with Peter Pan, Conagra Foods, peanut butter, and it's Salmonella Tennessee 529 cases. In from 2008 to 2009, the peanut butter is linked to the king nut, peanut butter crackers, and Salmonella triferium was the main cause, and 620 cases. So overall, estimated that total industry losses would be to be about $1 billion. So what is cold plasma? we are talking about atmospheric cold plasma, which means it's low temperature, low pressure, atmospheric pressure cold plasma. Is partially ionized gas at the near room temperature, used in various fields, including food safety, water treatment, sterilization, everything else you can think of. Some of the key characteristics, it's a non-thermal because it's a low temperature. That's a difference between thermal processing and non-thermal processing. I think most of you know about what all the different non-thermal processing methods, but a lot of interest has been going in towards the cold plasma recent years. And it produces reactive species like oxygen and nitrogen radicals. The microbial inactivation potential is the plasma generated species effectively disrupt the cell walls and DNA of the microorganism. And that's how they try to break the cell walls and become inactive. Some of the application of cold plasma, food contamination, foodborne pathogen removal. You can use cold plasma for enzyme inactivation. You can also use plasma for pesticide residue removal. And you can also use cold plasma as a medium or atmosphere where you can use it in food packaging modification so that you can extend the shelf life during transportation and also during the storage also. So what are the mechanisms of microbial inactivation by cold plasma? Basically, as I said before, when you use cold plasma, they produce reactive oxygen and nitrogen species, and these species play a critical role in damaging cellular components. You also produce UV radiation, and these are produced as a secondary effect of plasma. It can contribute to the microbial inactivation. And also, when you think about the plasma, it's also related to ozone. When you use the electrodes to create the cold plasma, what in essence, what it produces is ozone. So there are a lot of complex mechanisms going on when you use the cold plasma for food safety purposes. The electromagnetic fields are created, and these electromagnetic fields disrupt the cell membranes and led to the microbial death in the system. So this is what I have put together. We have put together here in a very schematic manner. You have microbial cell, reactive species acting the microbial cell. So there's a protein denaturation, and there is a nucleic acid cleavage and cell membrane rupture because of these reactive species. And due to that, lipid oxidation also happens. So you probably don't want to use this cold plasma in food which has a very high fat content, and you will have a lipid oxidation, and it will produce off flavor. So basically, the charged particles formed in cold plasma, reactive species, chemical and nitrogen species, and UV radiation also formed, and in visible range, and the electromagnetic fields are created, and anions, cations also get created, and they disrupt the cell membrane, and that creates the microbial death. So some of the advantages and disadvantages, when you look at the advantages, basically when you use cold plasma, it extends the shelf life, retention of nutritional quality. That's a key point here compared to thermal processing. In thermal processing, you tend to reduce the vitamins and nutritional quality of the food product, and that's why they started looking at the non-thermal processing method, including cold plasma. Residual free treatment, the half-life of cold plasma or ozone is very, very less. So within few seconds, or within a minute or so, or within few seconds, there is no residual cold plasma ozone is available in the system. It enhances the safety and the hygiene of the product. As much as we want to talk about advantages, it also has its own disadvantages. Equipment cost could be higher when you look at the industry scale setup. energy consumption also higher. We have to use a lot of electricity, high voltage electricity, and the skill requirement. We want to make sure that people who are using this cold plasma are trained to use these equipments. And cold plasma has a limited penetration. So you want to have a more surface area. If you have more surface area, then effectiveness will be much higher. So limited penetration cannot penetrate through the large thickness of the food product. Safety concerns also is there. When I say safety concerns, not in terms of the food safety concerns, but also the disadvantages when people are using it, if they are not trained, and if the cold plasma is inhaled in a large quantities, it could be lethal for the workers who is using these systems. We have been working on the cold plasma last 5 to 6 years. We tried different methods. We felt that plasma activated water worked very well. So the last 3 years, we have been working on plasma activated water. Basically, it's treating the water with a non-thermal plasma, and the non-thermal plasma is nothing but the bioelectrical recharge of gases like air or oxygen. You can also have any other combination of gas particles. And this process generates reactive oxygen and nitrogen species. And these contains these reactive species and are formed through the complex interaction between the plasma and the water molecules. So basically, that's how the plasma is created, and that's how the plasma inactivate different microorganisms. In this study, we looked at the salmonella and also the Intrococcus faecium. So there are two important microorganisms we tested, both salmonella and the faecium. I'm going to talk takes few minutes in terms of explaining the experimental procedures my students did. There are three different experimental procedures. One is using two different reactors, whether it's dielectric barrier electrodes or the other one is called BSD, both in situ treatment and also the ex situ treatment. In situ treatment is direct integration of inoculated sand into treatment, and the ex situ treatment is basically mixing inoculated sand with the plasma activated water for 5 minutes. Why we use this sand at low humidity? Because we want to create the salmonella and the faecium cocktails in low moisture systems, and we didn't apply these things in any food systems yet. Primarily, we want to test the concept of cold plasma and how different electrodes react in terms of making sure that the microbial inactivation is very high, or as high as 5 to 6 log reductions. So we did the in situ treatment, ex situ treatment, and also we tried to block the UV in the in situ treatment. So those are all the three boxes you see. So I'll be showing some results from these studies so that you can compare the how our results came out and what is our future activities in this area. So we use the very standard method of prepare the cocktails and applying them in the sand particles and doing the incubation and also counting of the bacterial colonies after this treatment. The system you see on the right side on the top right, that is our plasma system we used. It came from the University of Sydney. My collaborator, Dr. P.J. Cullen, has a business, and he is manufacturing these units, and there's a lot of people using the system throughout the world. So in this study, we used two different plasma reactors. One is bubble spark recharge, which is called BSD. The other one is dielectric barrier recharge. with the filter to make small bubbles. The idea here is the bubbles spark the charge. You can see on the left side, you can see the pink light. That's the spark. That's when you have two electrodes, and you create a spark, and that is the cold plasma. So the bubble spark recharge has less surface area. The bubbles are a little more bigger compared to when you use a dielectric barrier recharge with the filter. We were able to make small bubbles, and that creates a more surface area. So in general, we found out that this dielectric barrier recharge method gave a better results. It's more effective compared to the bubble spark recharge. So some of the key variables we tested in this study are both Salmonella faecium, and we tried two different reactor types, bubble recharge system and dielectric barrier recharge system. We used two different gases, air versus oxygen. We used two different water types, tap water and deionized water. Overall, what we found out was deionized water gave a better results because of the clean water. Tap water might have some other impurities into that, and that's the reason. So, but I'm not going to talk. We are not going to talk more about that. Just for your information, if you are trying to do this kind of experiments, you want to make sure that you use the deionized water. And we also tested difference between in situ and the ex situ treatment. And also we had the UV shielding presence. What will happen if you have a shield? If you protected UV, will it give a better results or not? So that's what I'm going to show you in our result and discussion session. So when we say about cold plasma, is it really cold plasma? That's what I want to show you that. It all depends upon how much treatment, how much energy you put in. Typically, cold plasma works very well within a minute of time. But my graduate student want to try it out. What will happen if you keep treating this? When you keep applying cold plasma for longer time, what will happen? So what will happen is that's what you see here. The temperature will definitely increase to the extent where it is closer to thermal processing. So this is not what we want to do. So this is first trial she did, and using the dielectric barrier recharge at a frequency of 2000 hertz. And then in contrast, with the different frequencies, she found out that everything happens within 1 minute. So the results you see here is the increase in temperature is very minimal. There's no increase in temperature within first 30 seconds at 1500 hertz frequencies. The future trials they are trying it out is 500,000 and 1000 hertz frequencies, because higher the frequency, the more energy input you are going to give. So lower frequencies is going to give a less energy input, and that's what we want to see. What is the optimization here? What will be the optimized conditions for this type of treatment process? Some of the results I am showing here with both Salmonella and Faecium. This one is first preliminary study we did using the bubble spark recharge treatment at a frequency of 2000 hertz. Again, if you look at these figures here, you can definitely see that within the 5 minutes, when it go to 10 minutes, there is no when you use the Salmonella in situ, both the Salmonella and the Faecium, in situ method have a more impact than the ex situ method. So overall, in situ treatment is better than the ex situ treatment method, and that's what you see. For 10 minutes, 15 minutes, 20 minutes, there is no detectable microorganisms during it after treating with the cold plasma activated water, for that matter. And this figure shows both the Salmonella and Faecium over 30 seconds of PAW treatment using bubble spark discharge and dielectric barrier discharge. Overall, dielectric barrier discharge was more effective, primarily because dielectric barrier discharge has more surface area, and that creates more species, and that gives you more contact, more 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 contact area for breaking the cell walls in both Salmonella and Faecium. Again, what you see is the institute treatment is better than ex situ treatment, and then dielectric barrier discharge method is better than the bubble spark discharge method. This graph shows both Salmonella and the Faecium survival over 30 seconds time period in situ treatment using dielectric barrier discharge with and without the UV block. So what you see here is if you block the UV, the effectiveness is less because UV also work as one of the mechanism where it can enhance or provide a synergistic effect of treatment. So that's what we like to see. So more studies needed to really see whether it's only because of the UV inactivation or it's combination of both cold plasma and also the reactive species and also the UV UV blockage. So some of the future studies, we have been making some progress on the what happens to the reactive species when they form, can they escape through the exhaust system? So or they have to be in the water system. I think so far the results have shown that they have to be in the water system because the reactive species cannot escape the water system and go out as an exhaust. So and that's not what we have been seeing so far. So, but more studies will be done to confirm that we don't need to worry about how much species are escaping during the treatment process. And the new concept in this line of work is it possible to develop a process where we can have a continuous PAW generation, where we can keep sending stuff through that system so that we can really have a system available for the continuous treatment of different products with the different microorganisms, and that will be more win-win situation for the industry also, so that there's a lot of work needs to be done in this area. That's what you see here. On your left side is a tube where you can apply this water, and then the right side is what you see, the pink color is the electrode, and there is coils around that tube there, electrode. That's another electrode, so that you have positive and negative, and we need to reverse this so that it can work in gravity. Right now it's against gravity, but our new design will be different than what you see here. So this concludes my presentation. So overall conclusion is whatever you try to do, cold plasma is more, whatever happens, everything happens within a minute. So 30-second treatment is much more effective, and more than that is not needed. When you look at the different reactor efficiency, the double barrier reactor discharge method gave a better results for more efficient with the air, and both BSD and DBD show the nearly identical effects with oxygen. So basically, if you are going to use the air to generate cold plasma, it's better to use the DBD method than the BSD method. In situ treatment is more advantageous than the ex situ treatment, primarily because there are more reactive species interacting with the microbes in making sure that they are effectively inactivating the microbes. Water purity is also very important. So far, I mean, all the studies we have conducted, deionized water is much more, water is more important, is better than the tap water. Plasma versus UV light blockage. More research needs to be done because whatever we have found out that we were not able to really block just take the UV out and then only do cold plasma. And we also need to find out how much of this plasma with the reactive species with the UV is making the microbial inactivation. This concludes my presentation. I'll be happy to answer any questions you might have.